So welcome to this Meow seminar, which we have in the morning, Monday morning European time, and Marc Vinyals from University of Auckland will enlighten our Monday morning with some color and some sunflowers. So what's not alike? Marc, please take it away.
Thank you, Jakob. Yeah, so I'll be talking about this collection of fun results that we had with Susanna, who's probably well known by this group. Right, so let's start by talking about circuits. Right, so we know that proving circuit lower bounds is hard. Not for any function, as in there's this well-known result that if you have just any function at all, and you don't care about the specific function, then you can prove exponential lower bounds for circuits. And yeah, well, that's great. But when we try to prove lower bounds for circuits for some explicit function, it's not that we've been very successful. So for instance, in 84, we got this result, oh, there's some explicit function that requires circuits of size 3 times n. And it's like, oh, well, great. That's something. I mean, and that is not n. Then the next year, Razborov proved that there is some explicit function that requires now monotone circuits, so no negations, of size exponential. To be fair, he first proved super polynomial, and then the result got improved to exponential, but still, we're going to say exponential here. And then there was some other progress by Johan Hostad showing that constant depth circuits also require exponential size. So if you've got just a constant amount of layers, then you need exponential circuits. And they're like, okay, well, seems that we are making progress. We've got all these exponential bounds for restricted model of circuits. Surely we're about to prove general circuit lower bounds anytime soon. And well, then time passed and passed and passed, and best we can do, at least last time I checked, is 3.1 n minus O of n. So not great. We don't know much about general circuits. So that's why I'm just going to be talking about some restricted class of circuits. I'm going to talk about monotone circuits. But then, as I said, these are circuits. We've got AND gates, we've got OR gates, and we have no negations. But then let's see which kind of functions these circuits can compute. Right, so some very natural questions we could ask about monotone circuits is, first, what is the size complexity of any explicit function or some explicit function? And this is known, for instance, for clique. We know that clique requires exponential size monotone circuits. And well, if you were here last week, you probably heard that matching now also requires exponential size monotone circuits. This had been only super polynomial for a very long while, so it's great that we now have these bounds. Sorry, I might be getting something confused here. Anyway, I'll continue this and just say large monotone circuits. But the question is, do we require truly exponential lower bounds? So when I say exponential here, I mean something like exponential in n to the epsilon. And what I would like is something like, well, exponential on some constant times n, something like that. Then this is something that we don't know. We do have circuits that require exponential size, but we don't know about truly exponential size. And there's plenty of other things that we know about circuits and have questions that have been investigated. For instance, something that's very natural to ask is, well, do negations help compute monotone functions? What do I mean by that? I mean that is there some function that can be computed by small circuits, but not by small monotone circuits. And well, of course, the answer, if I don't say anything else, is, well, yes, just take any non-monotone function. But let's say that I ask you for a monotone function, so a function that doesn't require negations to compute. Do negations help in that case? And the answer in this case is yes, there is some function that can be computed by normal circuits with negations efficiently, but still requires exponentially large functions. But this is a well-known result by Tardos. There's also the question of, well, how many negations then do you need for circuits? What's the power of small negations? This has been studied. There's also the question of, well, how much does depth matter? And then you can define all these different depth circuit classes. So you start with constant depth and fanning 2. So that would be NC0, which can't do anything really. It's too small. So we're going to forget about that. But you can have constant depth and unbounded fan in and monotone. And you can have monotone circuits of logarithmic depth and fan in 2. And you can have unbounded fan in depth logarithmic. You can have then fan in 2 and depth log squared n and so on. And all of these classes form a hierarchy. And so we know how to separate all of these classes, for instance. Good. And there's also a few applications of monotone circuits. So even if you don't care about circuits just by themselves, one very nice application is that if you can prove monotone circuit lower bounds, you can also prove lower bounds in proof complexity. I think there was a question in chat. That's Jacob. Sorry, never mind. Right. So if you can prove circuit lower bounds, you can get proof complexity lower bounds from that. Yeah, so having talked about circuits, what is it that we prove in this sunflowers paper? We basically get better lower bounds for some of the functions that we already had good lower bounds for. And so that's what we get. Let's see a few examples. So there's the clique coloring function. So again, here we would have the input is some graph. And in fact, it's the edges. And there's two possibilities. Either the graph has a clique, and then we need to say yes. Or the graph has a coloring. And in that case, we're going to say 0. Now, assuming that the clique and coloring are separated enough that the two conditions won't happen at the same time, so this is well defined. What might happen is that the graph has neither a clique nor a coloring. In that case, we're allowed to say nothing, so it's a partial function. And yeah, the clique function is a particular case of that where, well, if there's a clique, then you should say yes, otherwise you say 0. And previously, we had lower bounds for these functions that were about exponential in n to the 1/3. So if you plug in this k being n to the 1/3, the lower bound, you'll get something like exponential in n to the 1/3. And we improve this, and we get lower bounds that are about exponential in n to the 1/2. And again, minus epsilon. So we're going from n to the 1/3 to n to the 1/2. Then something else, yes, by the way, interestingly, this was also proved very recently, in fact, in the same conference that this paper was first presented, by another pair of authors using fairly different techniques. Or maybe not. It's, yeah, that depends on how you see the approximation method. Okay, so more things that we show. We show lower bounds for the bit pigeonhole principle for the cutting planes proof system. So yes, I talked about circuits a lot, but I also talked about applications, and one of the applications that we get is this one. This follows about immediately from a lower bound from the coloring versus co-coloring function, where now again the input is a graph and the edges, and there's two cases: either the graph has a coloring, or the complement of the graph has a coloring. Then we have to distinguish between these two cases. And here, the best lower bound for coloring was n to the 1/4. Now we get this to n to the 1/2. For bit pigeonhole, best lower bound was n to the 1/8. We get this to n to the 1/3. And again, worth mentioning that there were improvements made to the bit pigeonhole principle, also very recently. This is somewhat different in that this other result, they get slightly worse lower bound, so n to the 1/4, but it's something that works for the weak pigeonhole principle, or rather the weak bit pigeonhole principle, while we only get this for the strict pigeonhole principle, where you've got n+1 pigeons and holes.
Mark, could you say anything more about the parameters for coloring, co-coloring? Are you claiming that are there like two different numbers of colors, or it's the same number of colors, or?
Number of colors is Q. So there's a Q coloring. So this parameter is saying how many colors you have.
Okay. Thanks.
So it works for number of colors about square root n, which is fairly similar to how size of cliques would be when you're distinguishing between coloring and clique.
Okay, thanks.
Yeah, thanks for the question. And finally, we also prove better bounds for some function in P. So I mentioned before this question about do negations help? So is there some function that can be computed with normal functions with negations with circuits of polynomial size, but requires exponential monotone circuits? Well, the bound that you get for that is n to the 1/6, and we improve this to n to the 1/3. And to be fair, it's not that these results are that big, and it would be very nice if we could get a truly exponential lower bound for one of these. What I find the most interesting about these results is that they come from lifting. So you go through communication complexity, few reductions, and this is the surprising bit in that usually one would think of going through communication as wasteful, and reductions again as, yeah, chances are that your parameters are not going to be great. But yeah, surprisingly, it turns out that even though we are using lifting and communication complexity here, we are getting, well, not only matching bounds, but better than what we used to have. All right, so let's now go and talk about proving these results in more detail. So how does one usually prove circular bonds? The standard technique, again by Rasborov, is this approximation method where you've got your circuit and you say, I'm going to find a gate so that if I remove that gate, the output of the circuit is not going to change too much. Right, so I've got my circuit and I go to my other circuit with one fewer gate, and this computes a function f, this computes a function f prime, and f prime are close. Now, you keep doing this, making these local changes every time that you remove a gate. And if you can prove that, yes, every time that you remove a gate, the function does not change much, and after removing all the gates from your circuit, you will end up with, well, nothing. So it will be a circuit that just computes a constant function. And if you started from a function that was far from constant, such as the clique function, well, that tells you that in order to get a constant, you had to remove many gates, just because every time that you remove the gate, the function didn't change too much. That's a very high level overview of approximation method. Now, what I just hinted was that we were not going to do that. We were going to go through communication complexity. And what we're going to do is say, well, if you've got a small monotone formula computing of some function, and now I say formula in the sense of a tree-like circuit, then you can get a communication protocol for a certain game. And so let's go and see that. It's called the Karshmer-Witgerson game, or Karshmer-Witgerson communication problem, which is the following. We have some function, Boolean function. I'm going to describe the monotone version of the game. There is a non-monotone version as well, but that one we don't know anything about. So I'll just talk about the monotone one. And we've got two players, Alice and Bob. Alice is going to get an input for the function that is a one input, by which I mean that the function evaluates to 1. We'll have our other player, Bob. Bob's going to get an input that evaluates to 0. So, of course, these being different inputs, they must differ in some coordinate. And in fact, because the function is monotone, we know that, so not only they differ in some coordinate, but there's some coordinate where Alice must have a 1 and Bob must have a 0. And now what they'll have to do is, well, find such a coordinate. We're going to charge them for that, the amount of bits that they communicate. So here's a picture and an example of a function that we're going to see, which is again the clique coloring function. So what would be the Karshmer-Wiggerson game in that case? Well, the function, clique coloring function, is 1 if the graph has a clique. So we're going to give Alice a clique. Right? So Alice has this graph. Here's a clique. It's the same underlying graph. The only thing that changes is the edges, which is the input to the function. And we don't need to tell Alice where the clique is. We're assuming that these two players are all powerful, so they can compute any function that they wish. So if there's a graph and there's a clique, Alice is going to find it. That's no problem. Then Bob is going to get a graph. The graph is going to be colorable. So here we've got 3 clique. Here we've got a graph that is 2 colorable. So if we're thinking of the 3 clique versus 2 coloring function, then Alice's input would be a valid 1 input, Bob's input would be a valid 0 input. So then we know that there must be some coordinate where they disagree, right? And that means that Alice is going to have a 1. That means Alice has an edge. Bob is going to have a 0. Bob does not have an edge. So their task in this graph problem is, well, yeah, please go and find some edge that Alice has and Bob does not have. So that would be this edge here in yellow. And how are they going to do that? Well, they send messages. For instance, maybe Alice starts by saying, oh, vertex 1 is in the clique and vertex 2 is in the clique. And now Bob will go and look at his graph and say, oh, well, I've got this edge. This is not very helpful. Please tell me more. And then Alice will say, oh, well, 5 is also in my clique. And now Bob will say, oh, well, if 5 is in the clique, then I know that 1, 5 is not an edge. So I can just go and answer, yeah, 1, 5 is the correct answer. So now they're happy. All right. Now, the fun thing about this Casimir-Wigderson problem is that there is an equivalence between circuits and communication complexity, meaning the amount of bits that these players require to find a coordinate where they disagree. That is the same as the minimal depth of a circuit computing the function. That's something that Casimir and Wigderson proved. Proof's not too hard. You just swap Alice by AND gates, Bob by OR gates, and things are going to work. And more interestingly for us, because we're not going to be talking about circuit depth, but circuit size, is that you can also prove this for circuit size versus protocol size. Now, what is a protocol size? It's very clear what it means for the amount of communication to be. It's just number of messages. Protocol size would be, well, think of the players communicating as a tree. So there's going to be Alice here, and her first message might be a 0 or a 1. Right, and then there's two possibilities. And now, depending on what Alice said, then maybe here Bob is going to say some message, or maybe if Alice sends a 1, then it's going to be Alice who speaks, and she sends another message. And we'll get some kind of protocol tree. So when I talk about size or protocol size, I mean the size of the communication tree. Good. And so now we've got that, yes, if you've got the monotone formula, you can get the communication protocol. Actually, we don't want formulas, we want circuits. So we're going to need something called DAG-like communication instead of just tree-like circuits. And it's not too important. I mean, all the important details already work for tree-like, so it's not that we really need that. But again, just for completeness, what would a DAG-like communication protocol be? Well, it's the same idea. Again, you've got this protocol tree where players communicate, but maybe some nodes are going to join each other. Now, we've got to be very careful with how we join nodes. So when we join nodes, we usually ask for nodes to have a specific shape. And by that, I mean, think of all the inputs that are compatible with this node. That can be described as a set. If that set has a reasonable shape, like a combinatorial rectangle, then we will call this a rectangle DAG. If it's shaped like a triangle, then we will call this a triangle DAG. And yeah, we need this in order not to be able to have any shape, in which case we would lose any control about what the protocol is doing. Anyway, the good news is that we can also have the same kind of result for circuits, as in not formulas, but circuits and DAC-like protocols. So this equivalence is also true. Then the next step is going to be lifting. And now we say, oh, yes, well, you reduced this problem about circuit lower bounds to proving communication lower bounds, but proving communication lower bounds is still hard. Let's do something easier, and let's try to prove things in query complexity. So if we had communication protocols, tree-like, then what we would do is prove lower bounds for decision trees. Since we are working with DAG-like communication protocols, we'll get something which would be a decision DAG or something that we will call with query complexity, which I'll define in a moment. Okay, so what is this lifting business? Right, the idea is that we don't know how to prove communication lower bounds. We would like to prove query complexity lower bounds. Those we know how to prove. So what we're going to do is say, let's take some relation, and our relation will have variables z1 up to zn, and we will transform that into a communication problem. And we will do that by replacing each of these variables in our relation by a copy of the indexing gadget. So indexing is this function that goes from some pointer plus some string, and it outputs one character of the string. Right. So if one of the inputs is a string, the other input is a pointer, and the output of the function is, what is this character? Now we'll take each of these variables, replace them by a different copy of this indexing gadget. And here's an example of how this would look. Let's consider the query problem called collision. You also know this as pigeonhole principle. And it's the following. You've got 4 variables. You've got 3 possible values. Of course, there's going to be 2 variables that share the same value. So the task is, now please go and find 2 variables that share the same value. And do notice that I am stating this problem as a CSP, as in there's 4 variables and there are 3 valued variables. So I'm not thinking you might be used to CNF encodings of the pigeonhole principle. This is not what's going on here, right? It's just 4 variables and alphabet of size 3. And yeah, as a query problem, you can see that, you would have to query at least as many variables as you've got values, because every time that you make a query, the adversary is going to give you a different value. Now, what would be the compose problem of this? Well, then we'll now have this problem pigeonhole composed with indexing of length 5. So that will mean that Alice is going to get 4 pointers, so 1 for each variable. So each of these is one of Alice's pointers. And there's 5 places where these pointers could be pointing to. Then Bob is going to get 4 strings. Each of Bob's strings is going to correspond to a variable. And they're of length 5 because we decided that that was indexing of length 5. And now what they do is, they put this together. So Alice takes her pointers, points to Bob's pointers, and each of these pointed to variables is going to be a variable from the original problem. Right? So an instance of this lifting problem gives us an instance of the original problem. And a solution to the lifted problem gives us a solution to the original problem. And it's not too hard to convince yourself that, if you've got a decision tree for the original problem, you can easily find a communication protocol for the lifted problem. So what the players are going to do is just simulate this decision tree. So every time that the decision tree makes a query, Alice is going to say, okay, this is my pointer. Bob is going to reply, this is what I have in my input. And they will know the value of that query, and they'll just continue doing that. Fun part is that this is essentially the best you can do. So if you've got a communication protocol for this lifted problem, you can get a decision tree for the original problem of roughly the same size. There's some loss, but not too bad. Now, this is not quite what we want, again. So this is talking about communication, that's depth, and decision trees. We don't want that. Again, we want DAG-like things, we want size. Good news is that, yeah, this is also known for protocol size and DAG-like decision trees. So same result. If you've got a protocol, communication protocol for this composed problem of some size, then you can get not a decision tree now, but something somewhat similar. That's now going to have width about log s. But what do I mean by width? Well, it's instead of having the normal query complexity where you can make queries and you make a query and you're done, you could consider a version of query complexity where you can make queries, but you are also allowed to forget variables. And then if you forget a variable, then, well, you're not going to be charged for it anymore. But if you query that variable again, then you might get a different answer. And now what you're supposed to do is try to minimize the amount of variables that you remember at the same time. So in a sense, it's a measure of query space, perhaps. And the reason we call it width is because of, Albert, who used this to characterize resolution width with this kind of game. Anyway, so now we've got this way to go from communication protocols into query complexity. Let's continue. So we've got full picture here now. We'll start with the monotone circuit. We'll so assume that there is a small monotone circuit. We'll go into combination protocol, then we'll go into decision tree. But wait, there's an issue here, which is that, so we've got a decision tree, so this is hard for some query problem. And now we've got this query problem composed with indexing, but we've got a circuit that's computing clique. Right, so here we've got the combination protocol is for the Karshmer-Witgerson game of clique. And these things don't match, so what we will need to do is do some kind of reduction between this Karshmer-Witgerson game of clique and this composed problem. Good, so let's go and see that. What we'll do is do this reduction. So say that we've got an instance of this composed problem, so pigeonhole composed with indexing, and see how to solve this using clique coloring. Right, so now what our players have are k pointers and k strings. Again, so these are inputs to the composed problem. Their job is going to be to build an input for this. So they have this, they want to build this. Right, so Alice will build a graph that has a clique. Bob is going to build a graph that has a coloring. The graph is going to be this m times k grid. And this is going to be much more clear with an example. So let's go and draw some pictures. So let's say that Alice has pointers pointing to 1, 3, 3, and 5. What she'll do is say, okay, well, these are my pointers. This is the graph that I'm going to build. So the pointers are laid out in a grid. So if you now go and draw the graph as a grid, then first pointer was pointing to 1. This is a vertex in the clique. Second pointer was pointing to 3. This is a vertex in the clique. This vertex is this vertex. This pointer is this vertex. Oh, and this is not a clique, so let's make it a clique. Good, now it's a clique. Right, so all that she did was select this subset of vertices in this grid graph. And so the dimensions, M is going to be the indexing. So this is M, this is the number of columns, number of rows, that's the number of pointers. Now what Bob's going to do is, well, he's got these strings. He just needs to lay out the strings in order and build a graph where, well, every vertex is colored in the same way that his string has. Again, very easy. He just colors every vertex the way it should do. And now the graph he builds is the maximum graph that admits this coloring. So whenever there's two vertices that don't have the same color, he's going to add an edge. So he'll keep adding edges everywhere. He is not going to add this one because they share a color, but otherwise add all other edges as possible. Good, and I claim that we're done. Why? Well, because let's say that the players find an edge that Alice has and Bob does not have. What does that mean? Well, if it's an edge that Alice has, then these 2 pointers must have been pointers that Alice had, right? So this pointer Alice had, and Alice also had that pointer. What does it mean for this edge to not be there? Well, it means that the only reason the edge was not there is because 2 vertices that they're joining had the same color. That means that in Bob's string, well, these 2 vertices had the same color. So we found then 2 vertices, or 2 characters rather, that are being pointed to by Alice, and they've got the same color. That means that we have found a collision and solved the problem that we wanted. So now if we think about it, we've done everything that we wanted, right? So we started with a circuit. We used Carson-Wiggerson, got this way to solve clique coloring. Now we showed how to solve this composed problem efficiently, but the problem is hard, and so that's it, right? So let's go and recap all of this. Oh, sorry, I forgot about that. Yeah, let me mention this. We need to use a sparse version of this problem to get better parameters. So what we're going to do is restrict the amount of colors that each individual variable can have. Right? So when I explained the problem, I didn't give you any restrictions. What we will need to do is say, well, if I look at the number of colors that each vertex can have, maybe I'm not going to allow all of the vertices to have all possible colors. So maybe I'll say this vertex can only have these 2 colors, and this vertex can only have these 2 colors, and maybe this vertex can only have these 2 colors. 2 is not enough. We'll need 3 colors. And yeah, this is something that it's not too big of a surprise in proof complexity. So we often use this version of the pigeonhole principle that we call the graph pigeonhole principle. And if we assume that this graph between pigeons or variables and holes or colors is an expander graph, then everything's going to work. So the same lower bounds are still going to work.
So how do I think about this? I will think of the alphabet as now, or the indices now, the order of the edge, whether I'm picking edge 1, 2, 3, or up to something.
Exactly.
And then I
So
define collisions by looking at age and sort of decoding that the ith edge from vertex V and the jth edge from vertex U, they collide, and therefore this is a collision.
very much so. Yeah. So what will happen is that now Bob, as you said, is going to have a string
You have it on
That's
the slide. Okay,
over 3
thanks.
to the n. Yeah. Yeah, you're of course reading my mind and seeing what the features was. I mean, it's a very natural question, right? What's the input going to be now? So yeah, what will happen is that now, if we look at one of Bob's inputs, it's going to be, well, do I have the first edge? Do I have the second edge? Do I have the third edge? And then there's this graph, and this would mean maybe this is color 100, and maybe this is color 200, and this is color 300, right? But this is public information, so Bob, if he knows that he's got the first edge, he knows that that's color 100. And Alice can also know that. But yeah, once you do this, reduction still the same. Just that you need to be a bit careful with this extra layer of indirection. Makes things a bit more complicated, but that's it. Okay, so now I think as promised, we can go and do the proof. What we prove is this version of lifting theorem that depends on the alphabet. So the formal statement is this, and important bits, or the only different bit with respect to previous lifting theorems, is that there's an alphabet appearing here. So that means that the size of the gadget is going to depend on the size of the alphabet. And the bounds that we get, right, is saying that if you've got a query complexity problem that requires with Q, then the size of the shortest or the smallest tag-like protocol that's computing the compose problem is going to have this dependency on Q. And yeah, if you had a 0-1 binary alphabet, this was known already. The only new thing is that we've got the alphabet here.
So I might be getting ahead of you again, but you're somehow trading off M for the alphabet size, right? I mean, for a large alphabet, now, wait, what happens? Yeah, do you want to say anything about the trade-offs between the parameters?
Yeah, no, it's very reasonable. So you'll want your gadget size to be larger than the alphabet. And so in fact, this is not something you can get rid of. So we do show that there are some examples where if your gadget is more than the alphabet, then there is no such lifting. And if you had an alphabet that's linear in the problem size, then you would need to have then gadgets of size linear times linear, so something that's like quadratic. But well, we're using a gadget of constant size, so alphabet of constant size, just 3. So that's why we are able to just use a gadget of linear size. And so the whole reason why we cared about doing this in a sparse way is that if you had an alphabet of linear size, then your gadget would need to be quadratic. If it's constant, then constant is fine. So a linear gadget is fine.
So there's a question in the chat also. Albert is asking how epsilon is quantified and where does it appear in the lower bound?
Right. I think you need some epsilon to be larger than thing this log mn. Don't remember exactly. So this is not the formal statement. I can tell you about this later. But yeah, the formal statement would be more of let me see. Yes. So let epsilon be so that it's large enough that done some measure, and then things are going to work. And Albert seems happy enough, or at least not angry enough, or not too angry.
Yes. So if I want to take the Gös and Sokolov et al., so what is their size of sigma? Their size of sigma is
It's 2, because it's a
okay.
binary alphabet. Yeah. Yeah, I mean, we prove this for any sigma. We only use it for 3, but it's, well, I mean, yeah, we can prove it for any sigma, so why not? Right, so assuming this, the proof would be as follows, right? So we start with this relation, which has query complexity C. So C being the number of colors. So you can think of, yeah, if you don't remember all the colors, then, and you make a new query, then you can always find one of the colors that's not in memory and query it. So this is easy enough. Slightly more annoying for the graph pigeonhole version, but can be done. Then we compose this with indexing, and this is the gadget size that we're going to pick. So number of colors to 1 plus epsilon. That's going to give us a protocol for the compose problem of size, C to the C. And the graph size that we got from the reduction was k times m, right? Where k was now size of a clique, which we can pick to be a number of colors plus 1 or something suitably sized. And m, which is the gadget size, is just c to the 1 plus epsilon. So if k is about the same as c and m is about the same as c to the 1 plus epsilon, what we get is this c to the 2 plus epsilon. Right, so now pick number of colors to be about square root of the number of vertices, and you get the lower bound. Okay, I do want to mention why is the size of the alphabet important. So here we go. We've got pigeonhole with k variables, c values, find the collision. And now a collision means a pair of variables, which is an edge in the graph. And so the size of the graph can be about same as the number of variables. Now, if we try to do this with a binary alphabet, say with a bitwise pigeonhole principle or something like that, right, then we've got this problem that, well, now trying to find a collision means that we need to have many variables in mind. So if you want to certify that you've got a collision between, so you've got C colors, and you express that in binary, right? You'll need log C many variables. And then you'll have to say, oh, well, these log n many variables, or log C, are equal to these log C many variables. And when you do your reduction, then the size of the graph is no longer going to be k, it's going to be k to the log C. And yeah, that's too big, doesn't work. And one could still sparsify things and then end up with an alphabet of size 4, perhaps. Sorry, or 4 variables, 2 on each side. But then that would give decent lower bounds, but we wouldn't be able to improve on previous bounds. Right. So how does one prove this? In fact, this idea of colorful lifting happens to not be new. if you read this paper of Raz McKenzie carefully, they were already doing colorful lifting. That paper's full of surprises. And they were doing the same idea. They were also studying the collision relation, and they proved tree-like communication lower bounds for that. And then for some reason, well, people forgot about that. And next kind of lifting theorems, they were proven just for the Boolean case, so for a Boolean alphabet. And many improvements were done. So it got done with better parameters, for more general cases, for this DAG-like setting. And the last improvement was done by, well, quite a few people on this talk, which was proving lifting using the sunflower theorem. And I think that you explicitly didn't use sunflowers, but still close enough. Doing that for something called triangle DAGs. And in fact, what we do is take this proof that's doing lifting for triangle DAGs and hack it so that it works with any alphabet. And there's not that much that needs to change. So there is some part where you need to argue that when you make a query to some coordinate, then it's possible to answer that query properly. So that's something that's called the full range lemma. This will make sense if you know about lifting theorems. Won't make sense otherwise. And this is the part where the sunflower lemma would be used. And you just need to use a sunflower lemma with a non-uniform distribution. So instead of using normal sunflower lemma would have a distribution 1/2. If you use a biased kind of sunflower lemma with probabilities that are biased to be 1 over your alphabet size, things are going to work. And the rest of the arguments mostly the same, really. So this is really the only place that changes. You need to be careful, make sure that things are going to work, replace 0 1s by sigmas everywhere, and few other annoying bookkeeping details, but really the only thing that is somewhat substantial that changes is this thing. I'm going to skip some slides and just go to the end. Here we go. So yeah, what did we see? We saw some lifting with large alphabets, and we use, again, this large alphabet to prove lower bounds on circuits and on proofs. And yeah, there's this idea that sunflowers appear in many places. So they appear in the approximation method, they appear in clique lower bounds, they appear in lifting theorems. And well, then if all these methods are somewhat similar, is there some way to unify all of these methods and say, yeah, this is really the same thing? And informally, it seems that they are, but would be great to have some more formal theorem or statement. And then there's a question of, well, I mentioned that we proved lower bounds of form exponential of n to the 1/2. Could we get all the way up to exponential of 2 to the n with no exponents? And yeah, I'm going to stop here. Thank you.
Thank you so much, Mark. Thanks a lot. So, questions from the audience? So I'm still trying to understand how like this playing with the alphabet size explicitly. You mentioned this, but I'm still trying to wrap my head around why this is helpful. But maybe this is also something that we can talk about after the break if there's going to be a second technical half.
Yeah, it's other than if you try to do the reductions with a binary alphabet, and you see that you get worse parameters. Don't think I can say much more than that. I mean, maybe I could go to the relevant picture. Right, so here we had so we've got a collision that's just there's this variable, there's this variable, and it really is two variables, and you can uh, so an edge is between two variables. If you were
Mm-hmm.
doing this with a binary alphabet, I mean, since we can't do sparse pigeonhole with degree 2, we need at least degree 3.
Mm-hmm.
That means that each color would you would need to have at least 2 bits for each um, for each variable, right? And then you can't really say, well, I've got my 2 variables and my 2 variables, and I've got an edge, and I'm done, because the variables need to be grouped together in order to be able to say that if you've got an answer for your reduce problem, it's going to correspond to a solution of the original problem.
Mm-hmm.
And so what you will need to have is, instead of having one vertex for each um, character here, you would need to have um, vertices for, so you would end up having a quadratic amount of vertices that corresponding to this to pairs of variables.
Mm-hmm.
So a vertex wouldn't be a variable anymore. A vertex would be 2 variables, and the graph size would be larger.
Mm-hmm.
I don't know how much sense that made, but yeah, hopefully a bit.
Yeah, yeah, does. Thank you. Any more thoughts regarding your open problems? I mean, do you think this can be pushed to truly linear lower bounds, or are you looking for new ideas, or I
Yeah, I
mean,
think
what
that
about this unification?
we're probably starting to hit the limits of lifting here, in that if optimal lower bounds were to be proven using lifting, then we probably would need a gadget size of constant or logarithmic size. And that's a somewhat big open problem. And yeah, people think that it should be possible, but well, no one has proved it yet. But yeah, if one managed to prove lifting theorems with smaller than linear gadgets, I think that, yeah, this would be a nice consequence, but there would be even more interesting consequences. And yeah, these unifying methods are, I think that some people different than I have thought about them, and will have some smarter things to say.
Any more questions from the audience before we thank Mark again? So thank you so much again, Mark. And but do you want to say
Mhm.
anything about a teaser for if you would go into if there's going to be a second
Mhm.
half, and if like what kind of technical details can we expect? What's on the menu?
Yes, well, there's the other results we didn't discuss. So there's how does one do the bit pigeonhole principle, and how does one do any function in P?
Hmm.
And then uh, I will very strongly complain and say that there's absolutely nothing that changes in the lifting theorem. And if very hard pressed, I might flash the proof of that full range lemma.
Okay, it's good to know that we should prepare to see in which direction we want to push you. So again, thank you so much, and we'll now have a break. So we are now back after the break, and it's over to Mark again. Please.
Thanks. Right. So yeah, during the break we were talking about um, where the alphabet size came into play, and right, Jakob was wondering. Well, it seems that the smaller the alphabet, the better the lifting theorem is going to be. So why is it that we want a larger alphabet size? And yeah, the answer to that was that we would like to have smaller alphabet, but the reason we have a larger alphabet is so that we can lift a different version of the problem. And then we also went over the parameters with Albert. Anyway, so what's next? My suggestion is that I tell you how do we, or maybe I'll go to the beginning of this. Right, so we saw how to prove lower bound for clique coloring, but we still got bit pigeonhole and some function in P missing. So I can talk about these things. And I could possibly where are we? Yeah, show this full range lemma. Right? It would mostly be just look at what it is in the paper and give an idea of how one would prove this. Right? Any objections to that plan?
Sounds fantastic to me.
Excellent. Then let's talk about cutting planes, which I'm going to guess many of you know about. Right, so we want to certify that the formula is unsatisfiable. We want to do that using linear threshold functions. So if we got a formula in CNF, we're going to first translate it into some pseudo-Boolean form, which just means, yeah, we've got linear inequalities. And now we've got the following operations. We can always say that a variable is greater than 0 or smaller than 1. We can always take two inequalities and add them together. We can always take a linear inequality and divide it by some number, as long as we round up. And the goal is to, well, you start with a formula, do necessary operations, end up with 0 greater or equal than 1. Now, what we want to do is to prove a lower bound for cutting planes proofs, the size of cutting planes proofs of the bit pigeonhole principle. So bit pigeonhole is the following well, relation. So now it's the same idea as before with for collision, but now we've got the binary form of that. So instead of having a single variable with color C, now we're going to have log C many variables. And if you want to say that variable I has color 0, 1, 0, then you will say, well, that xi1 is negated and xi2 is positive and xi3 is negative. Right? And then what we say is just, again, for every pair of variables and every color, we say it's not the case that these two variables have the same color. All right, so to prove this, the idea is now what we're going to do is take a cutting planes proofs, go build a communication protocol, then do a communication reduction, and then do lifting. And now, well, the cutting planes to communication part, that's this result over here, saying that if you've got a cutting planes proof of some CNF formula of size S, then you can build the following object, a real DAG-like communication protocol for the falsifies closed search problem of F.
Just to compare, sorry, Mark, with like what Hrubesch and Pudlak would have done is they just cut directly to a communication DAG, which is a monotone circuit for the bitwise pigeonhole principle. So like no detour via lifting.
Yes, yeah. But so this would be Hrubesch, Pudlak. They would now go and prove lower bound for Carson-Vickerson. So that would be like a circuit lower bound. But we are going to go through lifting. But the first steps, which is cutting planes to communication and this communication reduction, that's the same idea.
Thank you.
Right. Just to define things, right? Falsified closed search of problem is you get input with some assignment, the output is some clause in the formula that is falsified by the assignment. And then this monster, real DAG-like communication protocol, well, it's DAG-like, meaning that, again, we've got this protocol tree that's not a tree, but a DAG. And the real thing refers to the shape of the nodes. So that means that if you've got some node in your communication DAG, then the shape of the inputs that are compatible with that node is going to look like a combinatorial triangle. And that just means that you can take Alice's inputs and sort them. You can take Bob's inputs, sort them, and then it's going to be monotonically decreasing or increasing depending on how you do things. Good. So that's the first step, cutting planes to communication. Then what Hrubesch and Pudlak do is say, but this bit pigeonhole principle, or the search problem of bit pigeonhole principle, is equivalent to the Karshmer-Wiggerson game of the coloring versus co-coloring function. And again, coloring co-coloring was you given a graph and Q, so Q would be fixed. It's not part of the input. And what you're supposed to do is say, well, is the graph Q colorable, or is the graph complement Q colorable? So I'm not going to do this step. What I will do is show how do we then reduce coloring, co-coloring to clique, co-clique. So now the idea is that we want to solve clique coloring, which we just prove is hard. And well, we'll do that by solving coloring, co-coloring. And here's how we are going to do that. So let's do Alice. And I'll just do a picture. It's going to be much more clear than looking at all this notation. So Alice has got this graph that is a clique. And maybe let's say that this is the clique. So this 3 vertices are part of the clique. The other 2 are not part of the clique. Right? That's the kind of input that she would get from clique coloring. And then what she'll do is build the grid. And things are somewhat misaligned. Now they're slightly better. And then for each of the rows where there's no clique, she's going to add the clique. So we've got this, and there's a clique. And for each of the columns that remain, then she's also going to build a copy of her original clique. Then what Bob does is say, okay, I've got the coloring. So I've got the same graph, and scored like this. So let's say that this is black is 1, white is 0, or well, blue is 1, white is 0. And he's going to build the following coloring. So we've got this parameter R, which is how many layers of grid we had. Then he'll start by saying, well, this is 1, this is 2, this is 3, this is 0. 0, then he'll say this is 0, 1, 2, 3. 1, he'll say 1, 2, 3, 0. 0, he'll say 0, 1, 2, 3. 1, he'll say 1, 2, 3, 0. Yep, so the idea is that there's this base coloring, which is 0, 1, 2, 3. And then if the color is 0, he adds 0 to everything. If there's a 1, he adds 1 to everything. If this was a 2, right, then this would be 2, 3, 4, 0, 1. Right, but let's go back to that. So that was 1, 2, 3, 0. Right, and now, so we've got that Bob's graph is now, well, colorful, because that's the coloring. So he's going to again build the most densest possible graph that has this coloring as a coloring. And then what Alice has is a bunch of disjoint cliques. So disjoint clique is the same as a co-colorable graph. Right? So if Alice is going to have this many disjoint cliques, so n would be here the number of vertices the graph started with, k is the size of her clique. So we've got n minus k, this is the number of these kind of cliques, and then r is the number of these kind of cliques. And so that means that it's an n minus k plus r co-colorable graph. And now my claim is that if we've got a solution to this R coloring, co-coloring, we've got a solution to the original graph. So why is that? Well, let's think what would happen. Right, so these bottom cliques, if we look at Bob's input, but he'll never have edges that sorry, he'll always have edges here. That's because these have different colors, so we can have edges here. So these are not going to be solutions. So the solution must be somewhere here in one of these cliques. And then what we'll have is, again, some edge that maybe will be this one, or some non-edge. But it's a non-edge, so it's joining two vertices with the same color. And then, well, two edges with the same color, that means that they had to come from Alice's clique. And then they will just say, oh, well, then solution to the original graph was this edge. And they had they had to have the same color, because if they were in the same column, if the colors had been different, then these columns would have been shifted. So this would not be possible. Right. So this is how you reduce clique coloring to coloring co-coloring. And now it's, well, we showed how to prove a lower bound for this. And so now we get the lower bound for coloring co-coloring, get the lower bound for search of pigeonhole, and that means we get the cutting planes lower bound.
Isn't it a problem that the number of colors is not the same? One is R, the other one is N minus K plus R.
This thing? No, it's not a problem.
The previous slide, you said the same number of colors.
And you could always set R so that these numbers are the same.
Well, not quite, because the right one is bigger, isn't it? K
yes,
is at
because N
most.
is larger. Yes. Sorry. I think that just by playing with parameters, you can then get this with the version where colors are the same, with the number of colors are the same. It's just some counting that I forget how is exactly. Quickly checking the paper.
Sounds like something that we might want to do offline. I mean, this would be the idea, is what you're saying.
Yeah.
Do you actually need the same number of colors, or maybe close enough is enough? Because if you make R big, then you can get close enough.
Yeah, I think you don't really need the number of colors to be the same. And Shio says, do you only need the product to be greater than n? And he might be right here. Um, I think that's right. Anyway, yes, good thing to do offline.
Okay, thank you.
Good. So other thing is, how do we prove that some function in P has lower bounds? And yeah, so there's this theorem by Tardor saying that there is some function that can be computed by normal circuits of polynomial size, but requires exponentially large monotone circuits, even though the function is monotone. And in fact, more carefully, what the theorem says is that there is some function that's yes, monotone, computable in polynomial time, and the function is a total extension of the clique coloring function. So the clique coloring function is a partial function, right? When the graph is neither has a clique nor is colorable, you can answer anything. If you make that a total function, well, it can only become harder because you're saying, yes, I don't compute just any extension, compute this particular extension. So the lower bound still applies. And yeah, so the reason why the lower bound, so the upper bound comes from theorem, lower bounds come from clique coloring. And if we just do the same thing, so we've now got better lower bounds for clique coloring. So exponential on n to the half. Because clique coloring has n squared many variables corresponding to edges. So if a graph has n edges, n vertices, then it has n squared many variables. So the lower bound is exponential on n to the 1/4 in the terms of number of variables. But we can do better than this. And here's how. The idea is that we don't need the full clique coloring function. It's enough to just consider a small subset of the edges. So if we look at our reduction, again, maybe I should go to this picture. What happens is that Alice is never going to set edges that correspond to rows here, because he only has one pointer for it. So there can be edges that correspond to columns, so two pointers might have the same value, but she only has one pointer, so there's only one vertex per row. So we could assume that all of these edges get set to 0, because this is never going to be a solution, they just get set to 0. And then for Bob, right, so Bob is going to add an edge when two vertices have the same color. But now we're doing graph pigeonhole. So if I've got this vertex and it has colors 100, 200, and 300, and I've got this other vertex and it has colors 400, 500, and 600, then Bob will always add an edge in that case, because we know that these two vertices will never have the same color. So the maximally adding an edge here will never break anything. So that means that we can take the clique coloring function, restrict some of the edges, and get fewer variables than what we would begin with. Right? So if we do that, then we set all of these Alice variables to 0, all of these Bob variables to 0. Then instead of having k times m many, k times m squared many variables. So k times m would be the size of the graph. Again, that was k, that was m. So k times m squared edges. We can get just k times dm squared, so where d is the degree, and this was just the constant. So we will get something that's k times m squared, and that will give us something that's n cubed. So if we go back here, right, so we had that the number of variables was, we got n to the 1/4. Now what we get is n to the 1/3 by using this trick. Right, so these are the main results. And I could go and, as I promised, show what the full range lemma is. We'll go and do that. Where do we have the full range lemma? Here we have the full range lemma. So the idea is that we are doing our lifting. How do we do lifting? Well, we have these players communicate and we measure them. So we look at how much information do we know about Alice's side. So we measure the mean entropy of a set of compatible inputs. So mean entropy would be this measure. And so we want to say that for each subset of coordinates, there's enough possible pointers that Alice has. And then what we want to do is say every time that they communicate, this mean entropy is going to decrease. And at some point, they're going to identify some coordinates so that they need to query those coordinates. And when there's a query, we want to make sure that all possible answers of that query are still possible. And this is what this full range lemma needs to do. So what it does is say, yes, if all these technical conditions happen, then there is some input corresponding to an Alice input. So that will be a set of queries. And then for every possible set of answers to those queries, then there is still some input that Bob has so that the communication problem can still have that answer. So this is what we would get in the query world. And then it's saying, yeah, there's this pointer where the solution to the all of those queries are still completely undetermined. And yeah, so this is the part where the alphabet comes in, right? So now we've got and not just every output to the queries that are in 0, 1 to the n, but we've got this sigma to the n. Then the way the proof works, I say, okay, well, let's assume that we've got a set of Bob that's too small, and we'll find a contradiction. So you can say, okay, let's assume that Bob, that this is not true. So there is some result of the queries so that, yeah, so I mean, order of quantifiers, right? So we want to say the negation of there exists this X star, so that for every beta there exists blah would be, well, for all Alice row there exists some answer to queries, so that for all of Bob's inputs, the Bob's string disagrees with the result of the query. And then as well, if that happens, then in particular, Bob's set can't have more than this. Yeah, so this is just encoding this. So this would be the maximum possible size of such a set. So it's inputs or strings on alphabet sigma. This is length of the gadget, n is number of variables. Again, so that for all Alice strings, Bob strings disagrees with the query. Now, using some monotonicity lemma, you can say that, well, I can actually just go and fix the result of the query to be just the string that's all ones. And that you would do by, well, here we go. So that's this claim here. And it follows by thinking of this as CSPs. So each of these constraints that has a fixed thing is going to be either independent or is going to be just the same as a previous query, where on the left, the constraints might have overlaps. So left side would always be smaller than the right side. Then we just write this as a probability statement. And then we notice that, well, if we're saying that this probability when y is being picked uniformly of being different from 1 to the n, that's the same as saying, oh, well, let's now change the alphabet size to binary and have biased probabilities instead. So if we've got these strings and they can take sigma possibilities, and we're just saying we care about, well, what if they get a 1? Well, then that would be the same as saying, so instead of having many colors, we're just going to say, well, now I still will just have an alphabet of size 2, ones and zeros. And now instead of picking this uniformly, I'll just say, oh, well, I'll now only pick 1 with probability 1 over sigma. And then once we've got this, it's like, oh, well, this expression happens to be the same as the sunflower lemma, just rewritten in a different way. So this would be the proper statement of the, so this is what we have. This is the sunflower lemma. and sunflower lemon is true. So that tells us that size of the set is too small, but our set, we assume that it's larger than that, so contradiction. And yeah, everything else from the lifting theorem. So the same ideas work. It's just replacing 0, 1 by sigma.
So this is a very vague question, but is part of this alphabet trick to somehow make sure that you don't leak partial information about symbols? I mean, because suppose like
Very much.
you could define your, I mean, you can always write down your alphabet. Like if you have a large alphabet, encode it in binary, right? But then I guess what the problem is that Alice and Bob can now try to figure out like the ith bit of your symbol, and then you have to keep track of like if they know the first bit of this and the second bit of this and the third bit of this, can they do some weird correlation? But here you're somehow like, no, no, no. Either you queried this symbol and then you know it's one of the symbols from 1 to C, or if you didn't query it, then you know absolutely nothing. There is no like, I don't need to keep track of bits of. Is that part of what's going on?
Kind of. I mean, in the communication world, you can always have these weird correlations. But in the query world, you're completely right that no, if you query something, you queried it. You didn't query the first bit. So, yeah, and that's why that is really why the larger alphabet is.
So, any more questions to Mark from the audience?
I have one question. So in the lower bounds, you mentioned lower bound for clique function, not the clique coloring function, which was slightly better. What are the hard graphs in that lower bound?
For us, it's the same. And for previous bounds that I don't know.
So just the clique and no other edges. That's the hard graph. And because it's a monotone function after all, right? It's obvious. But then what is the other graph? Okay, so I guess what I'm asking is, what are you separating? Graphs that have cliques from graphs that don't have cliques, or is it something else? Like in the case of coloring, it's not just graphs that don't have.
You can it's graphs that have k-clicks from graphs that don't have k-clicks.
Okay, so and then how do you construct the no examples, the graphs that do not have cliques?
So you just the same graph that has a small coloring, and that means that it doesn't have a clique.
So it's the same function then. It's again clique coloring.
Yes, for us it is. So I know that
Ah,
in the past they had used they had better bounds for just the click function because it's a harder function, right? You're supposed to distinguish between uh, yeah, the gap is more narrow,
yes.
and I don't know what the difference was. So,
Well, that's okay. So if you manage to do it with coloring, then yeah, that answers the question. Okay,
yeah,
thank
no,
you.
but maybe someone can come with something more interesting and uh, what the heck what? So I did mention that there was this paper. Here we go. In CCC where they talk about they also prove lower bounds for the click function. And here, so they do think some approximation version of the problem. And I do think they talk about only the click function.
Okay.
And do you want to say, so because I also wanted to ask about that, you said that whether it's a different paper or the same, like different techniques or the same techniques or how similar they are depends on your perspective. I mean, can you say anything more about that?
Yeah, no, I mean that ties to the open question, right? As in, uh, is the approximation method the same as lifting or not? So they use the approximation method in their paper.
And what the connection would be somehow that when you do lifting, you typically like you in every step you need to do a cleanup to get like well-structured objects to continue, and this would somehow be making sure you can do the cleanup nicely enough is somehow making sure that you can approximate nice with small enough error. Is that somehow the very loose intuitive way you want to connect the two, or should I think about
With
it in some
enough
other
hand
way?
waving, yeah.
Yeah, no, no. Generous hand waving, I think would be okay. Anything else? Otherwise, I'm thinking that we have already had lots of colorful entertainment from Mark with a very nice slide background also, which I noticed only very recently. Um, so thank you again, Mark. Thank you so much for this
Thank you.
presentation.
Thank you all for coming.